Hello guys, today we are going to do a question with 3 sessions. Part 1, part 2, part 3. So first we are going to evaluate the integral from 0 to 1 of sine a ln over ln where a is greater or equal to 0. Yes. We see the denominator is ln and here we got a ln. So we are going to let I of a is equal to the integral from 0 to 1 of sine a ln divided by ln and then we're going to differentiate both sides which respects to a. So differentiate this, you get cosine a ln and then times the extra ln. The ln and the ln cancel out, so you only get the cosine a ln here. So we are going to evaluate this from 0 to 1. Yes. And here is the deal. I would like to use the real part method. So whenever you see cosine, you just need to think about RE, the real part of e to the power of I times something. Yes. And then this time is a ln. We just put it as a ln here. And then here, because of the ln properties, you can put the IA inside the ln. So you can cancel the E and ln. So you can get this one will be equal to the real part of x power of IA. Yes. And then because of one of the property of the real part between the integral side, so you can put the RE outside the integral. So the real part of x to the power of IA dx. So to do this integral, we are going to add up the power and then divide it by the new power. Yes. So you can get 1 over IA plus 1 times x power of IA plus 1 power of, and then evaluate from 0 to 1. So 1 power of anything is equal to 1, right? And then minus 0, so it's just 0. So 0 power of that thing, just 0. Yes. So we are going to get just this, the real part of IA plus 1. So whenever we are going to find the real part of 1 divided by a complex number as the a plus bi form, whereas our b is greater than 0. Yes. We are going to multiply with the conjugate, and also the real part shouldn't be 0 as well. So we are going to multiply by the conjugate of it. So we can get the top, we get IA minus 1. And then the bottom, we are going to get this square. I square is -1, and then times a square, and then minus 1 square is plus minus 1 square, so it is 1. So we are going to take the real part of this. The real part of this pretty much just this one. So overall you get 1 over a square plus 1 here. And then we are going to integrate both sides. We are going to find I of a, right? So this is the original integral. So I of a, integrate this, you get inverse tangent a. Remember the formula, and then plus the constant. Because we are doing indefinite integral, so we have to add a constant here. And to find this constant, we are going to let a is equal to 0. This is the easiest one. I of 0. Put 0 into it, you get the entire integral to be 0, and then inverse tangent 0, you get 0. So in conclusion, we get our constant is equal to 0. So therefore our I of a is equal to this one, the original integral, right? So we can get this integral is equal to inverse tangent a. Really cool, huh? Yes. This is just our first part. We are going to start the second part. The second part is proof sine power of 3x is equal to 1 over 4. If we trying to go from here to here, it's hard, right? Because we have a 3 here. If it didn't have a 3 here, we can just subtract it and then do more work. But we have a 3 here. And when you are going to go from sine power of 3x to here, it's hard as well. So what I'm going to do to use our Euler's formula once again. Yes, Euler's formula is a really cool invention, but it helps us to do the real part of the integral and the imaginary part of the integral. We are going to use the real part method. It comes from the formula, the Euler's formula. Yes, thanks to Euler. Yes, he's really cool. So to find our e powers, because you know that our Euler's formula e power of ix is equal to cosine x plus I sine x, right? So when you plus 3x into it, 3x, I times 3x, you're going to get cosine 3x plus I sine 3x, right? And then also, because you know that e power of ix is equal to that, so we can power of 3 both sides. And then this and this gonna equal, so we can get cosine 3x plus I sine 3x will be equal to cosine x plus I sine x 3. Yes. So here we are going to use the triangle method, right? Something plus something and then power of 3. We are going to use the triangle 1, 1, 2, 1, 1, 3, 3, 1. Yes. So first you're going to get cosine power of 3x and then plus 3 times cosine and then minus the power and then time I sine x and then plus another 3 and then cosine x power of 1 time I times sine x squared. And then lastly we get 1 here, so I sine x power 3. So we are going to get something like cosine power 3x plus 3. I'm going to write sine first and then time cosine square x and then time I here. I'm going to write it as this way. So and then we are going to I square is equal to -1, so we are going to get a negative side here, -3 and then sine square x times cosine x, and then finally we get I power 3. I power 3 pretty much you get -I. I'm going to write this as minus sine power 3x and then time I, like that. So real part, we can get the real part is just equal to cosine power 3x minus 3 sine square x cosine x. And then our imaginary part is gonna be 3 sine x cosine square x minus sine power 3x times I, like that. Compare both sides, you can get this is our imaginary part. Sine power 3x is our imaginary part, which is just equal to this. So we can get sine 3x is gonna be 3 sine x cosine square x minus sine power of 3x. We are going to get something. We are going to get rid of this cosine square x. What can we do? We are going to change it into our 1 minus sine square x, right? And then distribute it. First you get 3 sine x. And then 3 sine x times this, you get 3 sine qx minus another sine qx, you get minus -4 sine power 3x, like that. So the original question needs us to prove sine qx is equal to this. So let this to be our subject. So we can get, I'm going to write the therefore notation. 4 times sine qx is equal to 3 sine x, and then distribute and the minus sine 3x both sides. Yes. And then finally divided by 1/4. You can just get this formula. Yes, just proof. The proof is proved. Yes. 1/4 times 3 sine x minus sine 3x, like that. This is just our proof. So we are done. So we are going to move on to the last session of this question. We are going to evaluate this integral. This looks kind of complex, right? ln over root 3 divided by ln x dx. First, we're going to use the formula sin qx is equal to 1 over 4 times that. So we are going to use this formula. Sin qx, which is equal to 1 over 4 times 3 sine of the inside ln x divided by the square root of 3. And then minus sine times 3 times this thing. 3 ln x over square root of 3, we can get square root of 3 times ln x. And then divided by another ln x. Yes, so many ln x here. So here we are going to split it to two different integrals. So we are going to get 3 over 4 times the integral from 0 to 1 of sine. And then here I'm going to write this ln x over square root of 3 as our 1 over square root of 3 times ln x, and then over ln x dx. And then subtract our. I'm going to restart it over again. I forget that 1 over 4 because we distribute inside. So we can get this integral is gonna be our. This is the one answers. This is inverse tangent of 1 over square root of 3 minus 1 over 4 times inverse tangent of square root of 3. So let me just do this faster. We factor out the 1 over 4 and then 3. And the inverse tangent of 1 over square root of 3 pretty much just pi over 6. And then we are going to minus pi over 3 here. So you get pi over 2 here, pi over 2. So 1 over 2 minus 1 over 3. And then divided by 4. We can get this equal to 1 over 24. So pretty much you can get the integral is equal to pi over 24. Yes. Wow. So this our result, pi over 24. Yes, this is really cool. In fact, look at this integral sine power of 3 ln x over square root of 3 ln x. If this constant between ln x isn't 1 over 3, and except for the numbers which is smaller than 0 or equal to 0, and 1 over 3 is the only result that can get rid of the inverse tangent, because 1 over square root of 3 you can just get a pi over 6 and just you can get the closed form of the pi and get rid of the inverse tangent sign. But whenever you put other constant like 1, you probably just won't get, you still see the inverse tangent sign. This looks ugly, right? Even square root of 3 you can't at all. If this constant is square root of 3, you still get an ugly result. In fact, this the 1 over square root of 3 is the only beautiful constant that can make this that greater than 0. 1 over 3 is the only constant that greater than 0 can make the inverse tangent disappear. Yes. So this is the fun fact. And thank you for watching this video, and I hope you guys enjoy this video, and peace.